Okay, so hello once again. Thank you for joining this technical webinar on managing service level objectives. My name is Thomas Pustai. I'm a PhD candidate at the Distributed Systems Group at TU Wien in Austria. And I and my colleague Philipp Reit will do this webinar for you. So let's have a brief look at the agenda. At the beginning, I'm going to briefly explain what service level objectives or SLOs are and how to handle them, and the concepts of the Polaris Framework, which is the component of Rainbow used to handle the SLOs. Then I will do a demo and show you how to generate and implement a composed metric controller and an SLO controller using the Polaris framework, and how to configure an SLO using Polaris. And then my colleague Philip will show you how we can take everything one step further and actually use metric predictions for proactive scaling. Okay, so let's dive right into it. Concepts of the Polaris framework. A little bit of background from cloud computing. We all know service level agreements, or SLAs, are commonly used to define bounds within which a service has to operate. And an SLA generally consists of one or more service level objectives, or SLOs, where an SLO is a commitment to maintain a particular state of the service in a given period. That means SLOs have to be measurable, but nowadays they're often limited to simple capacity guarantees, such as CPU usage or response time or uptime. However, we've noticed that high-level SLOs, such as, for example, the overall efficiency of the workload, would be much more suitable as business key performance indicators. And this is what we want to realize using the Polaris framework and inside Rainbow. So in general, each SLO on a conceptual level requires one or more metrics as input. So the metrics are like CPU usage, memory, and so on. They are exposed by the workload that's running, so by our service. And the SLO will periodically evaluate if our workload conforms to to our goals. If not, so if the SLO is violated, then it will trigger what we call an elasticity strategy. So this can be, for example, horizontal scaling, so adding more instances of the service. What we commonly see in production use today is the scenario down here. This example is based on the Kubernetes horizontal pod autoscaler, which is the most commonly used autoscaler in the Kubernetes world. There we have a CPU or memory metric that goes into an average SLO. So in this case, average CPU, that's the most common one. And it is tightly coupled with a horizontal scaling strategy. That's what horizontal pod autoscaler, or HPA, has been doing for a couple of years now. Recently, they have added support for custom metrics, but this requires additional setup and maintenance effort, and you're still limited to either an average operator here or a strict equality operator here. So this part here is still not very flexible, and you're tightly coupled to horizontal scaling. So with Polaris, we want to loosen things up a bit, and we have decided to decouple the SLO from the elasticity strategy. Now, this gives us the possibility to easily introduce new SLOs, which can, of course, be based on other metrics, and reuse them with the same elasticity strategy, or use a completely different elasticity strategy, because we no longer have this tight coupling. So we can, if, for example, we can change the average CPU SLO to use vertical scaling, or some migration strategy that will move to another node if the current node can't handle it. So this gives us additional flexibility. Now, this brings us to Polaris. So Polaris is a framework for building and customizing all these three components that you have seen on the previous slide and which are shown up here using TypeScript. It is available as a standalone framework, and it's also integrated into the Rainbow platform where it is used to enforce elasticity requirements. One of the central goals is to decouple SLOs from elasticity strategies so as to increase the number of possible SLO and elasticity strategy combinations. And as I mentioned, it's tightly integrated into the Rainbow platform. So over the next few slides, we're going to take a brief look at each of these components up here. We're going to start out with metrics. Polaris, of course, supports low-level metrics like all the other autoscalers do as well. So you can, of course, do something based on CPU usage, memory usage, and all the dozens or hundreds of metrics which exist. But high-level SLOs usually need higher-level metrics, which are not directly observable on the system. And that's why we've come up with the concept of composed metrics. So composed metrics are an aggregation of multiple lower-level metrics. And they can either be computed directly by the SLO or by an external controller and then shared through a common metric storage. Composed metrics can also be used to predict future values of another metric because they're a nice abstraction, so we can encapsulate some prediction logic there. And we'll take a look at all of this over the next few slides. So here we have an example with a resource efficiency composed metric. So in this case, we relate the resource usage to the total costs that's incurred by our workload and compute what we call a resource efficiency. And so we start out with an efficiency SLO controller, and this controller, of course, once it has been applied to a workload, needs to get the efficiency of this target workload. We have an abstraction that we call a metric source, which is supposed to do that. Now, this metric source can either compute everything right in here inside the SLO controller, or it can abstract away a more complex action, like in this case, fetching the information from a metric store. So the metric store can be a time series database like Prometheus, for example, or it can also be the Rainbow distributed storage. And it can store raw metrics and composed metrics. So how does the composed metric get into the metric store? That's what we have, this resource efficiency controller here. Its job is to fetch the raw metrics for our workload and combine them with the total cost of the workload. Now, CPU and memory are raw metrics, but total cost is another composed metric. So we can actually nest these composed metrics. This total cost composed metric source, again, goes to the metric store to fetch the total cost of the workload, which is periodically computed by a distinct controller. In this case, we call it total cost controller, and it's based on the cube cost framework. Once the efficiency controller has all the information, has computed the resource efficiency, it will write this information to the metric store so that our SLO controller can fetch it. This is the what we call reactive metrics use case. So all these metrics are computed based on what we're observing, and we only store the aggregation of these observed values. But we can take this one step further and add some prediction logic to this controller here and turn it into a predicted metrics controller. So this is used to add support for proactive scaling. And remember, Polaris is written in TypeScript. So here we use a polyglot approach with a small TypeScript wrapper around the Python AI code, because AI developers usually prefer Python. So we can have each developer focus on his strengths. So Polaris users will often be cloud developers who are familiar with TypeScript, whereas AI developers are often familiar with Python, and they can just focus on their part while the cloud developers handle the integration. Once we have the metric, we can then move on to the SLO. So for the SLO, we, of course, also need a controller that performs the evaluation. And the Slo controller basically runs an evaluation loop. And on each iteration, it will get the input metrics to check if the SLO is currently fulfilled or violated. If it is violated, then it will trigger a user-configured elasticity strategy. And with Polaris, you have the advantage that these SLO controllers are very easily buildable, because all this scaffolding around the evaluation loop, the triggering of the elasticity strategy, that's all done by the Polaris libraries, and you only need to write the SLO business logic. So, for example, to write an efficiency SLO, the one that I described in 2 slides ago, you only need to write this much code here. And actually, we will take a closer look at this during the demo. So if an SLO is violated, we said that it needs to trigger an elasticity strategy. An elasticity strategy will modify a workload's resources, possibly the instance count of the workload, or even the configuration. That depends fully on the elasticity strategy. Out of the box, in Polaris, we have horizontal scaling and vertical scaling. Rainbow adds a migration elasticity strategy as well that can migrate a workload from one node to a better performing one. But in general, with the Polaris framework, new elasticity strategies can be very easily built because we have automatic generation of all the scaffolding. And we also have base types which can be further customized. So for example, if you want to just write a customized horizontal elasticity strategy, you only need to calculate the new replica count, as you can see here in this little example. Okay, so now we have a metrics controller, we have an SLO controller, we have an elasticity strategy controller, and we have target deployments that we want to enforce an SLO on. So how do we do that? In order to do this, we have what's called an SLO mapping. An SLO mapping is basically a configuration object that establishes the relationship between the SLO itself, the target deployment, and the elasticity strategy. So this is what actually gets the whole thing going, because all the other things are just controllers which implement the logic, but this little SLO mapping actually gets the rock rolling, and it's something that you can configure with the Polaris CLI or also through the Rainbow user interface, of course. This mapping thing is a very important concept because we don't just use it for SLOs, but we also use an analogous mapping concept for composed metrics to trigger the composed metric controller. So a quick word about type safety. One big issue, if you just want to configure an SLO and a scaling strategy with YAML or with JSON, is you don't have any type of validation. And since we're using TypeScript, we can actually define various types for the components. So a service level objective will have a certain input configuration type, denoted by the yellow color, which defines which SLO targets it can support. So for example, an SLO might be limited to databases only. Then you shouldn't be able to apply this SLO to a REST service. And likewise, we have something similar with the elasticity strategy. It also has, each elasticity strategy has its own configuration type. And the bridge between these two worlds, the worlds of the SLO and the elasticity strategies, is the SLO output type. So each SLO can define a certain output type. By default, we ship a generic output type called Slo Compliance, which we recommend to be used by most SLOs because this maximizes compatibility between SLOs and elasticity strategies. But you can, of course, define your own type as well. So Polaris can be used as a development ecosystem, actually, because it comes with a very powerful CLI and with development containers. So with the CLI, service providers, developers, and consumers can generate all the mapping types and controllers and they just need to implement the business logic. This helps us lower the entrance barrier for new developers, and this will hopefully, this easier onboarding will hopefully lead to more adopters so that we can further evolve Polaris as time goes on. And the approach that we took, because we reused actually an existing CLI framework called the NX CLI, this allows actually combining Polaris-based components with other projects or components in a mono repository, because NX is a popular mono repo manager. Last but not least, this here is mainly targeted at developers and service providers who want to write new SLOs and configure them. Rainbow users can, of course, leverage the web UI to configure existing SLOs. So now we're going to show you a little demo about this reactive resource efficiency. So we'll have horizontal scaling of a deployment based on a resource efficiency SLO, and the metrics come from a real-world data set. So we extract them from Google cluster data sets from 2011. And the metric we use is resource efficiency. So we divide the used resources by the allocated resources. The goal is if we allocate some resources, we want to make sure we also use them so we don't waste money with resources that we don't need. And we'll trigger a horizontal elasticity strategy. So these are the components that we're going to write. We're going to create the resource efficiency composed metric controller. We're going to create an SLO controller and the SLO mapping and also configure it. The horizontal elasticity strategy already exists, and the target deployment has also already been deployed. It's just a dummy deployment, a Google POS container, because we extract the metrics from Google dataset. Okay, so let's get to the fun part. So here in the terminal here, I have already created a new workspace for creating Polaris SLOs. By the way, are there any questions regarding the presentation? Sorry, I forgot to ask. Okay, so we'll continue with the demo. And also during the demo, please feel free to interrupt me anytime. So I've already created a workspace for creating Polaris projects, because it takes about half a minute or 1 minute to download all the packages. So all I did was I executed the Polaris CLI init command and created the demo workspace. So we're going to cd into this now, and you can see a new workspace has been set up. All the configuration files are there. And yeah, let's take a brief look at what the commands that the Polaris CLI provides. So if we invoke it with help, you can see a quick overview of the commands that are offered. So we're mostly going to use the generate command today to generate new components. But we're also going to make use of deploying components and generating custom resource definitions, which we need to register our types with Kubernetes. So yeah, just one last thing. We're going to scale this deployment here, the POS deployment. Actually, as you can see, I've already been playing around with this today, so I need to scale it back to 1 replica. You always forget one thing when you do a demo. Okay, so let's start by generating a composed metric type. So we do this with Polaris CLI composed metric type, and we're going to call this efficiency. And we're going to add this into the project my SLOs. this project does not exist yet, so we're going to create it. There's, of course, documentation on the Polaris website for all these commands, so don't worry. And since we're in the TypeScript NPM world, we need to create an Npm package for this. So now it's creating a new library project with the efficiency composed metric type. And so one important thing is, since we have defined an Npm package name, we can actually publish this package to an Npm registry. So this means that other developers could reuse our types or our controllers in their own deployments. Okay, so we have generated it, and now let's open Visual Studio Code to open everything. Just a second. Okay. So we have my SLOs project, and you can see all the project configuration has been generated, so it can be compiled with just a single command and also be published to NPM with a single command. You don't need to worry about anything here. And this is the metric that has been generated. Let me actually zoom in a little bit so you can see it better. Yeah. So this is the file that has been generated for our efficiency composed metric. We have an interface that will be used to define the values of the efficiency metric. We have an interface that can be used to pass parameters to the metrics controller. Then we have an efficiency metric type, which will be used internally by Polaris to identify this metric. You normally don't need to modify this. And then the efficiency metric mapping is used, as I mentioned during the presentation, to actually tell the controller to get to work and to compute the metric for a certain workload. Up here we have a to-do list that we can follow in order to complete everything. Here in this case, we can just go very, very quickly and add a single property here to efficiency, and we call it efficiency. So the efficiency of the target workload in the range 0 to 100. And this metric actually doesn't need any specific configuration, so we'll just disable this warning. And then next, we're going to deploy this. So the next step is to generate the Kubernetes custom resource definition for our type, because it needs to be registered with our Kubernetes orchestrator. And we'll do that with the Polaris CLI gen CRDs command. Polaris is actually the first TypeScript framework that is capable of generating Kubernetes CRDs. So previously, most CRDs were written in Go, but we're the first ones to be crazy enough to do it in TypeScript, and it's working pretty well. So we can just apply this, and you can see it has been registered with our orchestrator. Okay, the next step is to generate a controller that will compute the metric. So we do this. Go away this. For some reason, I always get the tooltip here. Sorry about that. Polaris CLI generate composed metric controller. We'll call this reactive efficiency. And we need to tell it for which composed metric type this controller will be responsible for. So we tell it comp metric type equals efficiency. So we reuse the name that we that was used before when we generated the type. And we need to tell it the import path, my org, my SLOs. Just double check. Yeah, should be. Oops. No, forgot an S. It's not Polari, it's Polaris. Exactly, because I misspelled one thing. It's not import path, it's comp metric type package. And there we go. Sorry about that. So now it's generating a new controller with all the scaffolding that's needed to run a controller, to watch the cluster for new composed metric type mapping objects, so for new configuration objects. We only need to implement the business logic of the metric computation. By default, these composed metric controllers will expose their metrics to Prometheus. So today we are using Prometheus. We're not using the Rainbow distributed storage, because this is Prometheus is the vanilla solution that's implemented in Polaris. And so by default, these composed metric controllers will expose their metrics to Prometheus. And this is all handled automatically. But of course, it could be adapted to expose it to other databases as well. Okay, so we have now generated the controller, and we can see up here a new app has been added. Again, you have all the files needed to build it. You also get a Docker file that we will use later on to build a container image. And in the main TS file, you can see there's all the startup code needed. So it reads some environment variables from the configuration, creates a composed metrics manager, which is a component we use internally to handle all this evaluation. And it watches the Kubernetes cluster for new configuration objects. So you don't need to worry about anything here. Just go to the efficiency metric source. So remember from the presentation, a metric source is our abstraction for creating a or for supplying a composed metric. And here we can create one for the efficiency. Again, we have a list of to-dos that we can follow, or that we should actually follow. But to make things more quick, I'm going to go over to my cheat document here and just paste the code. Just don't tell anyone. So the composed metric source has two important methods, or at least this one here. Any composed metric source will have this get value stream method, which has to return an observable, which will emit a stream of the metric values. So as new metric values come in, this observable should emit them. Now, since in this case we need to manually query a database or a metric source here, actually, we use the get default polling interval method to establish an interval for polling our source. So, and here in the get efficiency method, we will normally implement the computation of the metric. Here we've taken a little shortcut. We just select the Polaris composed efficiency metric from our database. This is because remember, we're basing this example on actual Google Cloud data, which has been gathered by Google. So we're reading these data in another controller and computing the metric there to make things simpler there to extract the data. Okay, So we will save that, and the Polaris CLI can also be used to build our Docker images. So with this command, Polaris CLI Docker build, and then the project name, Reactive Efficiency, we can build the Docker image. Yeah, I'm actually going to cut this short here because normally it takes about 1 or 2 minutes, and yeah, it probably doesn't make sense to just look at the progress of the Docker build, because I have already pre-built these images, and we're going to deploy them. So if we want to deploy this, we can use the Polaris CLI deploy command, Reactive Efficiency, and this will deploy our controller to the currently configured Kubernetes cluster. So this relies on the current cluster configuration used in the kubectl tool. So whatever is configured as the default cluster there is going to be used for executing these Polaris CLI deploy commands. And let's see now if the deployment has worked. So, and here we are. So this is the new one. You can see it's been created 35 seconds ago. The other controllers are the ones that so these two vertical and horizontal elasticity strategy are shipped by default, and then these here are used for serving our Google cluster data. Okay, so one controller done, one to go. Let's continue with the SLO controller. So in order to create an SLO controller, we need an SLO type first. So we'll generate an SLO mapping type. And we're going to call this efficiency, and we can add this to the project my SLOs. Okay, so some files have been created, and we are kindly reminded that we should add this line here to the initialization function of our library. And we can do this very quickly. So the reason behind this is that actually Polaris operates on an orchestrator independent object model, and we have a transformer service in there which handles the transformation of the Polaris objects to Kubernetes native objects, and you need to register the types with this service. And this is done in the initialization functions of the libraries. Okay, so next we can take a look at the SLO mapping that has been generated. We have an empty interface that's used for configuring the SLO. We're going to fill this in just a minute. And then we have an efficiency SLO mapping spec class. So spec is usually used by Kubernetes to define what an object has to contain in payload. And you don't need to add anything to the body of this class, but the type information here is important. So it tells us which SLO configuration to use. It tells us the output type that this SLO will use, Slo Compliance in this case, and the input type, so the SLO targets that it supports. In this case, the most generic one available, SLO target. If we wanted to restrict the SLO a little bit, we could change one of these types here. And then the SLO mapping type here doesn't need to be changed. It's just it's generated so that later on the Polaris CLI can generate the custom resource definition. One thing that you may want to change, you can change the group here and use your own namespace, but for the demo, the default one is fine. Again, the cheat sheet. So the target efficiency is part of our SLO config and nothing else. And we can, again, generate our CRDs. Okay, one done, one to go. Okay, and here we are. Generated, and let's apply them to our cluster. Okay, so we reapplied the metric mapping as well. That's unchanged, and then here the SLO mapping has been created. Next, we can generate the controller for the SLO. So we can run Polaris CLI G SLO controller. We're going to call this efficiency controller. And we need to tell it where the SLO mapping can be found. my.org/my SLOs. And the SLO mapping type is called efficiency SLO mapping. Okay, controller generated. Let's go back to VS Code. So we have a new project here, a new sub-project, the efficiency controller, again, with Docker files and everything ready to go. Also, all the YAML files needed for a Kubernetes deployment, everything has been generated. And in the main TS file, we again have all the needed startup code. We don't need to do anything here. If we want to load additional metrics libraries, we could initialize them here, but in this case, just the one that we initially referenced, the my SLOs library is fine. So we don't need to do anything here. We'll just go over to implementation of the SLO controller. So again, let's go to our cheat sheet to keep things nice and quick and make sure everything's working. So don't mistype anything. Yep. So an SLO controller has two important methods. One is the configure method, which is invoked by the framework when a new SLO mapping is received from the cluster. So this reads the parameters and also obtains the composed metric source. And then inside the control loop, the SLO framework will periodically call the evaluate method, which is supposed to calculate the actual SLO compliance. Because in this case, we use SLO compliance as the output. If we were to use a custom type, we would need to compute the custom type here. The calculation of the SLO compliance is straightforward because we have a lot of logic in the metric sources. So we can just obtain the current value from the metric source and compute the compliance by dividing the target efficiency by the actual efficiency, and then make sure it's an integer because Kubernetes prefers integers. And then we return this. So just one quick word about SLO compliance. So SLO compliance is the default SLO output type that comes with Polaris and that we recommend to be used as much as possible for compatibility reasons. It has one important field, the current SLO compliance percentage. If it's exactly 100, everything is perfectly fine. If it's above 100, then we probably need to scale out or do something similar. If it's below 100, then we're outperforming the SLO and we should scale it in or similar. Okay, let's now build the controller. Again, the same thing as before. We're going to cut it short and just deploy it. Polaris CLI deploy efficiency controller. Has been deployed. Let's make sure it's running. Get deployments in Polaris. And yes, here we are. Efficiency controller is up and running. The last thing that we need, remember, in order to apply the SLO to workload, we need an SLO mapping, instance, you could say, because we have the type already, and now we need to create an instance. So let's generate one. Polaris CLI generate SLO mapping. We're going to call this demo efficiency. And we need to tell it which SLO mapping type it is. Efficiency SLO mapping. And the package. Okay, and here we are. Again, this is more the developer-focused part of SLO management in Rainbow. So this is if you want to create new SLOs, new elasticity strategies, then you want to dive into the Polaris CLI. If you just want to use what's already there, because we have very, very flexible generic SLO in Rainbow, you can just go to the Rainbow UI directly and configure this generic SLO through the Rainbow UI. But if you want something specific to your use case, or if you want to use Polaris in some other non-Rainbow related scenario, then you can use the approach that we're using right now, because it's very developer friendly, very code management friendly. You can check everything into source control and version it, and makes it very easy to use. So the efficiency SLO mapping, it's just an instantiation of the class. And a lot has already been generated, and we have some to-dos again. So first we enter the target namespace. That's demo in this case. The name of the SLO mapping will be demo efficiency, that's fine. We need to configure the SLO target. So this is a deployment. So the group is apps v1. You might need to look this up in the Kubernetes documentation, of course. It's fine. And it's called pause deployment. We could change to a different elasticity strategy, but in this case, we're fine with horizontal scaling. And we need to complete our SLO configuration. So in this case, we only need to specify the target efficiency. And we're going to make this 90. Additionally, we can specify a stabilization window. By default, Polaris uses a stabilization window of 1 minute to ensure that we don't continuously scale up and down, because that doesn't really make sense. But here we actually want to see something very quickly. So we're going to set this to just 10 seconds. And additionally, we can create a static elasticity strategy configuration to configure the maximum replicas, for example. So here we're going to use max replicas 3, maybe let's make it 10. Okay, and then we can just serialize this SLO mapping and pipe it into kubectl flag. And while we're doing that, maybe let's open a quick watch here on the deployments in the demo namespace. So we have one replica at the moment. Our efficiency SLO mapping has been created. And now we're going to examine the logs of our efficiency controller. Okay. So you can see here, it loads the configuration. And here it has successfully added a new SLO, the demo efficiency that we create, and it immediately started crunching the numbers. So at the moment, we have an SLO compliance percentage of 6. So this means that we're actually outperforming the SLO, but we're already at 1 replica, so we can't really do much more. So we're going to stay at that. But we have selected a piece of data from the Google dataset that will also cause it to scale out. Yes, here we are. So an extreme scale out here, as you can see, SLO compliance percentage of 636. So we definitely need some scaling. And as you can see here, we have gone up to 7 replicas. Okay, so that's it for the reactive part. Now my colleague Philip will take over and demonstrate some proactive scaling. Are there any questions regarding the reactive part so far? Okay, so please, Philip,
okay,
the floor is yours.
Thank you very much. I will share my screen now. I hope you can see it.
Yes, yes.
So yeah, thanks, Thomas. So far we have seen basically the main components of the Polaris framework and how to do reactive scaling. Now we want to reuse most of the components and want to scale with a proactive approach, namely with an AI model. And I will show you how you can do this with Polaris. So the scenario is as follows. We have a metric store, for example, Prometheus, that is basically calculating or at least exposing the efficiency, the resource efficiency, and the Elasticity Strategy controller takes this efficiency and scales up on it. What we have seen right now is the reactive approach, which uses the current usage of the cluster, and based on that scales up or down. And the thing I will present now is the proactive part, where we generate a predicted metric controller instead of a composed metric controller. And we use the current usage data to predict the future with an AI service. And we will cover both parts. So we will basically see how to create the predicted metric controller, as well as how to, or at least how we deploy the AI service and call it. And yeah, in the end, Prometheus scraps either one of them. So you can easily change your scaling strategy based on the controller that is deployed. So either you can have the composed metric controller deployed or the predicted metric controller, and it is transparent basically to the Elasticity Strategy controller. So just a quick note about our deployed model. So we have published 2 that are doing more or less the same, but with 2 fundamentally different neural network approaches. In either case, we use, as we've seen before, the CPU, memory, and I/O data from the Google Cloud set and predict the efficiency, which is then published or scripted by Prometheus. The architecture of the predicted metric controller looks as follows. So we have on top the composed metric controller, which is one package that's one container. And we have the so-called AI proxy, which is another container, and they both reside in one deployment unit. So in Kubernetes, this would be a pod. So both containers run in the same pod and call each other via localhost. So if the Prometheus metric store scraps the composed metric controller to get the resource efficiency, the composed metric controller will call the REST API of the AI proxy, which is written in Python. The reason why we use Python is simply that we want to give the developers, the AI developers, the possibility to use typical and mostly common machine learning frameworks, or at least the pre-processing features, because the prediction itself is done using an AI service. So the AI proxy exposes the REST API layer, then queries the raw metrics, for example, from Prometheus, builds the input features, and then calls the AI service with the pre-processed input features to retrieve the prediction. The green parts in the AI proxy are known or developed by AI developers, meaning they do not have to know any infrastructure knowledge. And the Polaris libs take care of everything else. So basically we divide the development cycle of this unit into two, namely the infrastructure part, the composed metric control on top, and the AI proxy, which is mostly done by AI developers who do not have to necessarily have knowledge about Kubernetes or any infrastructure. So before I will show you the live demo, I have 2 slides left, namely the prerequisites, so which deployment we have currently running, so you understand basically how it works behind the scenes. So to host the AI model, we use MinIO, which is an S3 compatible object storage. And on the other hand, we use TensorFlow serving, which is basically developed by TensorFlow themselves to easily host AI models and to offer a convenient REST API to call those models which we use. This is the AI service we've seen previously. And the next thing are the steps that we are going to see in the presentation. First of all, we generate the predicted metric controller. We're gonna implement the mapping between the AI response, namely the response that we get from the AI service, and the SLO metric. So obviously the AI service is not aware of any SLO metrics or composed metric types, so we have to convert this. This is done by developers that have knowledge about the infrastructure. We're gonna implement in the AI proxies the pre-processing of the queried data. We configure the deployment files, and then finally we can deploy it. So I will now switch over to my code editor. So we will start in the command line by generating the predicted metric controller. I will just copy paste it here, but basically it's as we've seen before with the composed metric controller. Instead we use the predicted metric controller, which auto-generates our application. So I hope it's clear enough. I have configured the editor to have at least an increased font. I can't change it sadly here. So what we can see here is the basic project structure of the predicted metric controller. We see here the AI proxy, which contains the Python files, and the source, which contains the TypeScript. We are going now to look into the mapping between AI service response and the SLO metric. We have reused the same definition of the SLO metric as Thomas developed before. So this is easily reusable, and you can have the reactive and the predictive parts in the same project without having to change anything. And basically what we can see here is now the source, which calls the AI service, or let's say the AI proxy, which is auto-generated for you. And you simply have to implement the interface, that is the API response, namely the response from the AI service, which is in our case a simple matrix. I will just copy paste the code here. And on the other hand, you have to map the response to the sample of the efficiency, the SLO metric that Thomas defined before. So in our case, we get the response and we just read it basically from the matrix, namely the first entry. And because the model currently predicts in floating points, floating numbers, we multiply this by 100 to have the same values as we have seen before. The next step, so basically this is all that is to be done regarding TypeScript and also regarding the infrastructure part. The next part is done in Python and targets the querying of data, the pre-processing of data, and the invocation. to give you a quick overlook of this AI proxy, which runs in its own container, we are using Flask as a REST framework. And basically we predefine, or yeah, it's all pre-generated for you, the rather simple sequence of fetching the raw input features via the query handler, then pre-processing it, and then invoking the inference, namely in our case, the TensorFlow serving instance. And in the end, we just return the inference results. So that's why we need to map the API response to our SLO metric. Yeah, the query part is actually also implemented for you. We currently provide a Prometheus-based implementation, so you can specify which keys, or let's say labels, you want to have in your input features. And then the pre-processing part is actually the first part where you have to implement your own code, because we are obviously not aware of any kind of pre-processing that has to be done. So this is domain specific to the model. I will just copy paste our stuff over here. I will not go into details because yeah, it's actually not quite relevant to the workshop, and can be looked up on the GitHub repository, because everything you see here is basically one-to-one on GitHub. But yeah, as I said before, we now here get the raw input features and pre-process it based on our model and return it. And there is actually not much more to do regarding this part. So meaning that we have now created the predicted metric controller, the TypeScript part, namely the composed metric controller, which is invoked or scrapped by Prometheus. And we have now also fully developed the AI proxy part. So in theory, we could now build this simply by using the Polaris CLI. I will also skip this due to time constraints. I will also use pre-existing containers, but as you can see here in the CLI, this is the command, and this is, I think we have seen it before too. And one thing that I want to show you before deploying this whole thing is the configuration of the deployment, meaning this is on the infrastructure side again. So there are some things that you have to configure to really deploy this thing. So what I will do now is, that is not something you have to do in general, but I have to, because I'm using pre-built images. So let me first copy paste the correct image here and also down here. But two things have to be configured in this YAML file that is deploying the pod. So it's a deployment, but it basically deploys a pod that is containing the TypeScript part, the composed metric controller, which we've implemented. And on the other hand, it contains the AI proxy, the REST API we've just finalized by implementing the pre-processing part. In the end, you have to do mainly one thing. You have to point the REST API, the AI proxy, towards the TensorFlow serving instance. Out of the box, we provide an implementation for TensorFlow serving, but it's rather easy to extend this for example, PyTorch serve. But I will just copy paste here the URL that is called when we invoke the AI proxy. So you can imagine this TensorFlow serving is running as a Kubernetes service in the background and is invocable over this API. And other than that, we don't have to do much more. We can actually already deploy this. So let's invoke the Polaris CLI, and I hope that everything is working. Yeah, So basically what we have now deployed is the pod that I'm mentioning all the time that contains of the TypeScript and the Python part. Let's check if it's also visible already. Yeah, so we have one predicted efficiency deployment, which is now also ready. Namely, we have one pod of 1. If you want to see logs of this, you can also do this. So for example, if you want to know what's going on, for example, in the AI proxy, let's see. Yeah, so basically you can already see in the logs that it's already calculating the metric, meaning that it fetches the current usage, namely the data from the data set, feeds it through the sequence of invocations we've just seen in the AI proxy, namely the pre-processing, calls the LSTM model that is deployed using TensorFlow serving, and returns this to the composed metric controller, which then feeds it into Prometheus. So now we can take a look into Prometheus itself, the composed. Yeah, so here we already have the metric ready, and I will just increase this. And basically, instead of calculating it in a reactive manner, meaning we use current usage, we are now using the model to basically predict the future usage based on the current usage, and therefore have proactive scaling. Yeah, that's actually all there is to this approach. I hope you liked the short presentation. And yeah, if you have comments, please let me know. Thank you.
Okay, thank you very much, Philip. Yeah, if there are no questions, would like to thank you all for being here, for attending the short webinar. I hope you enjoyed it. We will of course publish the recording on our YouTube channel, and you can also download the slides from the Rainbow website shortly. Thank you very much, and have a nice afternoon.